Hi, good day and Assalamualaikum. I am Muhammad Iqbalazhan bin Noor Azam and I will be presenting my final year project presentation on review and modeling of capacity-based sensor in medical application. I am under supervision of Prof. Dr. Hayati Saad and my panelists are Dr. Bulan Binti Abdullah and Dr. Sukarnur Bin Che Abdullah. Hope you guys enjoy my video. In this video, there are 10 contents of my research that I will be explaining of, which are introduction, problem statement, literature view, research question and objectives, scope of research, methodology, research results and discussion, and significance of research, and lastly, conclusion. Medical industries has been established since World Wars, and even in this modern globalization era, this industry is found to be very vital in older days because of the needs of medical supplies during world wars. The armies and soldiers used medications to heal themselves, but yet slow recovery against open wounds. Until today, human beings are still reliable to medications to maintain good health quality. Despite the pandemic COVID-19 issues still lingering the world, people who have gone seeking for medical aid, no matter those who are healthy or having symptoms. MEMS, or Microelectromechanical Technology, combines silicon-based microelectronics and micromachining technology. It consists of microsensors, actuators, and a microelectronic circuit. MEMS pressure sensors also cover the sensor major part market lately. The automotive and health industries are the most important application groups, accounting for more than half of the pressure sensor market in 2014. MEMS pressure sensor in particular accounts for 72% of sales, while other 12% coming from medical electronics, 10% from the industry, and the remaining 6% split between the consumer electronics and military aerospace applications. Now we move on to piezoresistive pressure sensor (ppm) versus capacitive pressure sensor (cpm). Because of its great sensitivity relative to other sensors, capacitive sensors have drawn a lot of interest. Pressure sensors are required in biomedical, environmental monitoring, and industrial process control applications. Capacitive pressure sensors, on the other hand, offer superior pressure sensitivity, low noise, quick reaction to pressure changes, and the ability to endure severe vibration, making them ideal for new high-performance applications. Furthermore, capacitive pressure sensors are outperforming piezoresistive counterparts in terms of power consumption, temperature sensitivity, and fundamental of noise floor. Piezoresistive pressure sensors have high effectability, allowing for direct action across a large pressure range, while capacitive pressure sensors are preferred because they have pressure effectability and execution that is temperature invariant for the most part, making them appropriate for high pressure and temperature applications. An adjustable membrane is used in MEMS pressure sensor to distort in the presence of pressure contrast, and the deformation is translated to an electrical signal. Now we move on to the problem statement of my research. The first problem statement is the research, which is reviewing and modeling of capacitance-based pressure sensor in medical application. Secondly is the cost. In real application, the cost to boot the sensor is considered based on the sensor's capabilities and performance, which means that if the performance and capabilities of the sensor is high, so that the cost to boot of the sensor must be high also. And the thirdly is repeatability. Sensitivity and the relationship between capacitance and pressure sensor will affect in the repeatability. If the sensor is insensitive enough, so that the repeatability of using the sensor is much lower. Next is literature review. In medical applications, various parameters can be defined using capacitive sensors vital in monitoring patients' health. There are four literature reviews that I obtained from, which are from Zaman, Khanna, Jah, and Nova. Zaman, he conducted a research on accelerometer, which this accelerometer is an electronic sensor that measures the forces of acceleration acting on an object. In medical terms, he conducted a research on the sensor used to measure an inclination of bed and chair positioning. And the sensor is good in sensing of objects' position and movement. Next is gyroscopes. Gyroscope is a sensing device uses Coriolis effect to determine the angular velocity, where the angular velocity is the change of rotational angle of an object per time. The thirdly is mass flow measurement. Flow sensors used to measure drug delivery and verification of respiratory function. And the term used is Coriolis mass airflow sensors, which quite similar to the gyroscope techniques they use, and the highly accurate and currently in use in operation theater drug delivery equipment. And lastly, pacemakers. Pacemakers is used to place under the skin of chest for heartbeat control. Electric stimulus, pH blood value, and blood pressure can be measured during pacemaker, which may need a capacitive sensor for high repeatability and good in performance. Now we are coming to research questions. My research questions are on the review, simulations, and the outcomes. The review: what preference need to be used before reviewing the journal articles related to the research study? Next is the simulation: how to model and simulate the sensor before applying parameters needed for the outcomes. And the outcomes: do the outcomes are gained with the research objectives or slipping away? My research objectives are to review all the microsensors that uses capacitance-based control in medical applications. Secondly is to model and simulate the capacitance-based pressure sensor using console multiphysics software, and to analyze what are the outcomes of simulation with the correlation of capacitance and pressure. The scope of research explains the extent to which the research area will be explored in the work and specifies the parameters within the research while operating. There are four focuses, which are reviewing microsensors used in medical application of capacitive-based concept. Secondly is how the capacitive sensors work, significance of sensors, and what are the types of sensors used. The thirdly is the functionality of the body to store charge in electric field, and unit is farad. That is capacitance. And the basic formula is C equal to Q over V, which is the capacitance work best with a potential difference V proportionally to the load required or charge is Q. We move on to methodology. There are several steps in modeling and simulating the sensors by taking these three elements into account. Firstly, journal article review. Before modeling of a sensor or a sensor is modeled and simulated, series of journals articles are reviewed, and we must study on the related research study topic. Second method is model designation and selection of materials. The capacitive pressure sensor is designed and the parameters are set up. Also, the materials chosen in console multiphysics software. Thirdly is the simulation of the sensor. After the model has set up of parameters, materials and values inserted, the models is computed for one-third simulation results. The first methodology is journal article review. It is very vital in collecting some information related to the research study, and not necessarily depending on journal article. Textbooks or Google Scholar web search engine are also used to find the related topics studies, and to get the outlines or ideas on how to start modeling the sensors. The next methodology is model designation and material selection. My capacitive-based pressure sensor is circular in shape and 3 mm radial size. The design is retrieved from console homepage under MEMS module application, which means that the design is based on the drawing provided in the console homepage, but the parameters and the values Also, the materials chosen are not included in the drawings. They provided only the drawings but not the values. The sensor has two electrodes, acts as the main element of sensor, and it is a circular plate concept model representing the movable upper plate and the fixed bottom plate. The parameters such as pressure is set up to analyze the effect of pressure with respect to displacement of membrane with the determination of correlation between the model capacitance and the pressure. Next, because of the geometry is symmetric, which refers to the circular hole structure and the square shape in the middle, it is sufficient enough to examine only one quadrant of the model, which is a 1 over 4 of the whole structure. The analyzed part, or the quadrant model, consists of a thin membrane biased to 1 volt potential. The vacuum chamber separating the die and the diaphragm, which located at the middle of upper plate and the lower plate. And the work principle of MEM capacitive pressure sensor works on electromechanics principle, which when the external pressure is applied on the thin membrane, the pressure difference of the cavity and the external applied pressure causes the deformation of thin membrane. And the thickness of air gap is now not uniform because of the applied pressure, and the deflection is transmitted to the electrical change in capacitance. As for the materials chosen, silicon is chosen as the sensing element for the sensor, and with the composition of 100% silicon, it proves that the material provides great strength to the sensor. Silicon material is applied to all domains, which means the whole structure, but the vacuum material is chosen as a dielectric medium between the two electrodes, the upper and lower plate. As for the sensor's base, steel IC4340 is utilized, where this type of steel is an alloy steel, low alloy steel that can be heat treated and contains of chromium, molybdenum, and nickel that gives the alloy steel a more toughness and strength. Upon selecting the material, properties must be filled, and the relative permittivity is the ratio of the capacitance with certain material over as dielectric with the vacuum as dielectric. Next is bonded parameters and material properties setup. The pressure at 25 kPa is set up because this pressure is maximum enough to deflect the thin membrane. The properties of silicon selected are inserted before running the simulation, or otherwise the material inserted cannot be recognized due to this value of this property, such as Young modulus, Poisson ratio, density, coefficient of thermal expansion, and relative permittivity. And the vacuum material is set up with relative permittivity of 1. And the steel IC4040 is the built-up material obtained from additional specified material in console. And again, the relative permittivity as in table of silicon properties and vacuum properties is the ratio of the capacitance capacitor with certain material as dielectric with a vacuum as dielectric. After the model parameters, material chosen, and the values inserted, and the outcomes of the simulations are shown. The Bose-Misser strengths on the thin membrane at a pressure of 25 kPa, and the result shows that the deflection is the greatest at the center of the membrane, where you can see at the red color stress shows that the deflection is the greatest at that uh, particular region. And on a slice of two capacitor plates, which means at the vacuum at the center of the upper and bottom plate, the electric potential is in the seed chamber is depicted, as you can see in the bottom figure. After the simulation had run and shown its results, the 1D plot line, one-dimensional plot line, shows that the maximum and the average displacement of membrane with respect to variety of applied pressure are shown in the top figure. where, for example, the displacement of central diaphragm at pressure of 10 kilopascal is 0.9 micrometer, and while at 15,000 pascal, the displacement of the central membrane is around 1.3 micrometer. And the bottom line plot shows the model capacitance versus the applied pressure. The correlation gain is that as the pressure applied keeps increasing, the capacitance increases but non-linearly. The one-dimensional 1D plotline shows that the diaphragm displacement and the capacitance of model can be obtained. As the capacitance of model is obtained, the sensitivity of model can also be obtained as shown in the table. The sensitivity is defined as the ratio of output signal and measured property. A sensor's sensitivity indicates how much the sensor's output changes with the input quantity being measured changes. For example, the pressure sensitivity is thus given by the formula of Sp equal to delta C over P, where delta C is the change of capacitance, while the P is the applied external pressure. The mechanical sensitivity is obtained by ratio of the pressure given by formula of Sw is equal to delta W over P, where delta W is the displacement and P is the external applied pressure. Next is the significance of research is to produce a very useful type of sensor that can be used widely in every sectors, useful in terms of long-lasting use, very durable, small and lightweight but quality, cheap to get, and can be used as wearable device among patients. And the target of future work application is to measure blood pressure. So the arterial pulse wave is a crucial sign in medicine since it's closely linked to physical features of the cardiovascular system. The sensor is positioned over the radial artery of the wrist to measure pulse waves and to demonstrate the capabilities of highly sensitive pressure sensor as in the figure. So the concept of this application is the same as the research study, where there are parallel plates that attach together, and by the vacuum that lives in the middle, so that it is worth noting that unlike the traditional methods, no compressive cause is necessary. The technology is well suited for non-invasive and continuous blood pressure monitoring because of this feature. Due to the fact that low pressure sensitive capacitive sensors do not require a cuff and may be simply worn on a wrist, a conversion of the capacitive signals or pulse wave into a pressure value must be performed. The sensor's quick response time gives excellent resolution, allowing it to extract specific clinical information from wrist pulse waves. A precise calibration between the observed capacitance and the pressure is required for monitoring blood pressure. So, this research suggests that the use of micro-electromechanical MEMS capacitive-based pressure sensor in medical applications, specifically for blood pressure monitoring. The corresponding displacement at the center of the diaphragm for a given 10 kilopascal just now pressure is found to be 0.9 micrometer during the simulation of capacitive pressure sensor, and the average diaphragm displacement is 0.28 micrometer. The simulation yielded encouraging results, including high sensitivity and size reduction, which could be used in a variety of MEMS capacitive pressure sensor applications. That's all for me. Thank you for lending me your ears. And if you have any queries, do contact me on my mobile number listed below. And also, I've provided my email for you to ask me for any doubts. And that's all for me. Thank you. Assalamualaikum and stay safe everyone.